I know that one thing that's important in your work, if I understand correctly, is that you have a set of axioms that you use as kind of the center of your work. And can you talk about why you use that kind of approach?
Okay, so yeah, so this is what happened. I mean, I should talk about my career really. I started off in quantum foundations. I did my PhD in from 1989 to 1992, and at that time the field of quantum foundations was very concerned with interpretations of quantum theory. How do you make sense of quantum theory? And there was all these different interpretations, like the many-worlds interpretation, where every time there is a quantum choice to be made, both things actually happen. The world splits into two copies with one thing happening in each copy of the world. And by the world, I mean the universe, everything. And there's the de Broglie-Bohm model, where the quantum wave function guides actual particles that exist, and these particles are guided along a path by this wave, and many other interpretations. And so that was what people were thinking about, and that's what I was thinking about. And I became a bit unsatisfied with that way of thinking, because it didn't really seem to lead to any new ideas. It didn't seem to lead to the possibility of real progress in fundamental physics. You took the existing theory and you tried to make sense of it. It was a lot like the ether theories, the mechanical ether theories. People took Newton's theory or Maxwell's theories and tried to make sense of those equations. But no, those ideas turned out not to be useful. And my feeling increasingly was that this wasn't a useful way of making progress in quantum foundations. And then I came under the influence of Chris Fuchs, and he was asking this question. He was saying, well, can you derive quantum theory? Can you derive quantum theory from some more basic ideas? He wasn't the first person to ask that question, but it was the first time I'd encountered the question. In his case, in particular, he was working in this sort of new field of quantum information, and he was saying, well, can you give an information theoretic reason for the axioms of quantum theory, for the structure of quantum theory as it was? And so I set about working on that. This was in 2001. And eventually I found a way to approach that problem. So the idea was to be very operational. What I mean by operational was to just talk about, what it is you do, the settings of knob settings and so on, and what it is you see, like detectors clicking, lights flashing. Yeah. So the operational approach is really just taking seriously. Experimentalists have to do experiments. They have to go into the world and put things in different places, set knobs to different positions, and read off the data. And so I set up a framework like that. And then furthermore, I add in probabilities, because quantum theory is all about probabilities. In the end, in some sense, quantum theory is a more natural descendant of classical probability theory than it is of Newton's theory. Quantum theory is a probabilistic theory. Mm-hmm. So I set up this way to write down sort of just probabilistic theories that pertain to operational situations. So you have an operational situation, you have probabilities, you can write down a mathematical framework that applies to that situation. Mm-hmm. And then once you have that mathematical framework, you can say, well, maybe I can find some principles or postulates, or I'll call them axioms, that constrain you. And, so say, initially you have all possible probabilistic theories, but now you want to specialize to particular probabilistic theories. And so the axioms I wrote down enough axioms that would get you to quantum theory. And that was work I did in 2001. So that was a very interesting exercise, and I felt like that kind of work helped to make progress. I felt like I was understanding quantum theory in a new way that I hadn't previously understood it.
You said you think all theorists should have to spend some time in the lab. Is it a different part of the brain that activates to work in a experimental setting?
Absolutely, yeah. I mean, like I said, I've never actually sort of actually got my hands dirty, so to speak, and moved these things around. But really, a laboratory looks nothing like a bunch of equations like these equations here. It's a completely different world from a laboratory, and you don't really understand physics until you understand that it is about the experimental world. It's about experiments in the end.
And would it be the same framework that you hope might give quantum gravity, but with a different set of axioms?
Okay, so yes. So what happens is I did that work in 2001, just before I came to Perimeter Institute, and then I came here, and people were thinking about quantum gravity. You know, there was string theorists, Rob Myers and Lee Smolin working on loop quantum gravity, and so quantum gravity was very much in the air at Perimeter Institute back then, as it is today. And I started thinking, well, perhaps we can take this kind of general probabilistic technique that I developed and apply it to the problem of quantum gravity. Otherwise, what is it good for? You know, it's a lot of fun to it's called reconstruct quantum theory. So you start off with some general framework, you write down some axioms, and you get quantum theory. But we already knew what quantum theory was, so it wasn't really pushing us forward. It was just providing a new way of understanding things. What would be a real test would be if we could start off with some general framework, apply some axioms, and get quantum gravity, a new physical theory. That would be a great test. So I started thinking about that. One of the problems was that the operational framework I developed wasn't really hospitable to a theory of quantum gravity. I realized you'd have this property of indefinite causal structure I mentioned earlier, that the order of events would be indefinite, but the operational framework had boxes with wires connecting them, and those wires were the direction of time. So a wire particle would leave one box and go into another box, and that would be happening forward in time. So it wasn't the right framework to treat the problem of quantum gravity. So I set about building a framework that would be hospitable to quantum gravity, I hoped. And this was a probabilistic framework that was capable of admitting indefinite causal structure. So I took a very general operational approach. I tried to really sit back and ask, what is an experiment? What do we do in an experiment? And how can we translate that into a mathematical framework? So in an experiment, what you do basically is you make choices, like I said, you set knob settings and you collect data. And so I imagined a mathematical framework that was capable of analyzing that sort of situation probabilistically, but very generally, without assuming any definite causal structure. And so that was work I did in 2005, and I called it the causaloid framework, because the central mathematical object in that framework was something I called the causaloid. And that's really driven all my research since then, is the attempt to formulate quantum gravity in this kind of more general mathematical framework. If you think about it, Einstein, when he was developing general relativity, needed a mathematical framework to do that in, and he was lucky that Riemann, 65 years earlier or thereabouts, had developed Riemannian geometry. This is the framework of curved spaces, and Einstein was able to take that mathematical framework directly and use it for general relativity. And so the question was, well, maybe we need some similar sort of mathematical framework, but for the problem of quantum gravity. So that was the idea. But that was 2005, and I'm still working on it. So it's not clear to me that that's exactly the right framework, but at least it was an idea, and it's something that came out of my earlier work on axioms for quantum theory that you asked about. And I did a PhD, and it just kept going. Once you start doing research in physics, you just keep going, and it's endlessly fascinating. Quantum theory is endlessly fascinating. It's constantly surprising. You think you've understood everything there is to understand quantum theory. You work on it for 20 years, 30 years, and then it surprises you yet again. So it's easy to keep going. It's really interesting subject.
Good morning. Do you feel axiomatic approaches allow for easier collaboration and mutual understanding, since everyone is coming from the same starting point?
Okay, it's a good question. Let me think about that. I think that's right. What these axiomatic approaches do is they force you to clarify very basic concepts so that you can talk to other people. And you end up having to clarify these concepts outside of the natural habitat of quantum physics. So an example would be, in quantum theory, you have Hilbert spaces. You don't need to know what Hilbert space is, but it's an object that has a dimension, n. Okay, so n is an integer. It can be 1, 2, 3, 4, etc. And that's just a number that appears in quantum theory. But if you want to understand what that concept really means, then you should think about it in operational terms. And what it really means in operational terms is what are the number of preparations that you can prepare for your system that can be perfectly distinguished. So by thinking in operational terms, you're forced to clarify concepts that might have just been elements of an obscure mathematical framework. And I think that's true not just for that example, but there's many concepts like that that help collaboration. They help they help people make progress in physics, I think. Yes.